And in fact, this data here enables us to kind of just allude about what's going on. So here we've got some really nice data, which was from Spencer and colleagues. And what they've got is the ATP concentration is maximal sprint exercise. So this is doing 14 seconds of exercise. And what you can see here actually is they're from kind of different time periods. This is done with muscle biopsies. But actually, there isn't a massive reduction. It goes from around about 25 millimoles per kilogram per decimeter, and it goes down to about, well, let's be about 16 millimoles. So we've had about a 40% decrease in the ATP concentration itself. So one of the things to understand is that we never really run out of ATP, because fundamentally the whole process of metabolism is to find ways of resynthesizing that ATP. Here you can see what happens to the PCR concentration over that same time course. So it falls from about 80 millimoles per kilogram per decimeter, and it ends up at around about 40 millimoles per kilogram per decimeter. So we've actually had a 50% reduction in the PCR concentration over this period of exercise. So although perhaps not a depletion, you can see there's certainly a significant decline in the PCR concentration. Now this is really important because we understand that this happens really pretty much with all substrates, that they start off with a very high concentration, and that concentration just starts to decline over the course of the bout of exercise. What is interesting though is over that same block of exercise, it's only a 12-second period. Here we've got the lactate concentration. Now, one of the things to say at this point here is do not be fooled into thinking that lactate is by any means bad. Lactate is not bad, lactate is not a byproduct, and lactate is not a waste product. What the lactate is showing us here, it's a reflection of glycolysis. So let me explain very briefly what we mean by that. So to do that, we're just going to flick back through a couple of the slides. So if we look at the process here, and if you look at the center, you can see the process of glycolysis, either starting with glucose or starting with glycogen. And as we said, if it's under, in inverted commas, anaerobic conditions, the end product of that is the pyruvate gets a hydrogen ion added to it, and what we end up with is lactate. So lactate is our proxy indicator of glycolysis. So the higher the lactate concentration, the more energy is being derived from the anaerobic metabolism of glucose or glycogen. So the lactate is being used in this example to show us how much glycolysis has contributed. So of course what we can see is over the time course of the study, or this exercise, is the lactate concentration has gone up from around about 10 millimoles per kilogram per decimeter, and it's got up to around about, well, it depends which data point you take, anywhere from about 60 to 70 millimoles. It's got a six-fold increase. But what you'll notice is, as the PCR concentration goes down, the lactate concentration goes up. PCR goes down, glycolysis increases. We're running out of PCR because we've got a limited capacity. We've got a bigger capacity, but our rate at which we derive the energy is slower. And the fact that the rate at which we derive the energy is slower will, as you're about to see, come at a cost. So if we look at this really nice schematic, again, which was provided by Heck, it's really useful. Then what it shows us is the way in which the energy systems interact with each other. So in this example here, we've got a block of exercise ranging from about 10 to 14 seconds. This is maximum intensity exercise. The key bit to look at is in the middle. You can see the PCR concentration. Now this isn't about rate. This is absolutely about the capacity. So how much of these substrates are used. Not about rate. It's about how much is used. And what you can see is at the onset of exercise, we've got a PCR concentration in this example here of about 20 millimoles per kilogram. By the time we get to 12 seconds, and I want you to be focusing here on just the smaller dashed lines, just the smaller ones. By the time we get to about 12 seconds, that has fallen down to around about 2 millimoles per kilogram. But what you'll notice is, although that is falling, again, reinforcing what we've been alluding to already, a number of the other traces are increasing. So if we look at what is called DLA-DT, which is delta lactate delta time, that is the abbreviation in this example for glycolysis. Again, look at the small dashed line. At the onset of exercise, almost within the first second, there's an increase in the rate of glycolysis. Again, reinforcing the idea that the energy pathways are working simultaneously. And as we get to around about 4 to 6 seconds, you'll notice that the PCR concentration, the rate of decline, starts to slow down. That curve it's had a very steep fall, and then it starts to slow down. At around about 4 to 6 seconds, you'll notice that the glycolysis, the rate at which glycolysis is operating. Sorry, because this is a rate valued one, because this is delta lactate delta time, therefore it's got a time variance, is increasing. So we're accelerating the rate at which glycolysis is being operated, because it's trying to increase its rate to compensate for the fact that the PCR concentration is falling. Simultaneously, you'll see that the lactate concentration is increasing. And remember that the lactate concentration is a reflection of how much we are using glycolysis. So what we would know is that because the rate at glycolysis is accelerating, which is reflected both in the abbreviation, which is delta lactate delta time, and in the increase in lactate, what we would know is that the stored levels of glycogen are starting to decline. At the same time, you can see the pink trace reflects VO2. That's the volume of oxygen. That's the proxy indicator here in mils per kilogram per second at the rate at which oxygen is being used. So this is just merely reflecting that there is an aerobic contribution, again reinforcing what we saw from the Mark Hargreaves data earlier on, that there even at the onset of exercise, even if it's high intensity, there's an aerobic contribution. The final thing to look at is at the top of the chart. You'll see pH. And the pH is here to reflect the cellular environment. And what you can see is that as time increases, the pH starts to decrease. Now, conventionally, people will suggest, well, that's because the lactate concentration is going up, and that lactate leads to cellular acidosis. That is not correct. So we could quite simply take any of you and basically put a line into one of your veins, and we could pump sodium lactate into a muscle cell. The muscle would not show any change in the pH. It's not the lactate that causes the change in the pH. The change in the pH is caused by the presence of hydrogen ions. Hydrogen ions are the byproduct of metabolism. Hydrogen ions serve two really important purposes. One of the purposes is that the hydrogen ions, as I've already alluded to, the hydrogen ions are used to help us resynthesize ATP. So hydrogen ions are produced during glycolysis. They are also produced during the aerobic metabolism of glucose in the TCA cycle. The hydrogen ions are, under certain conditions, are shuttled in pairs down what is called the electron transport chain. And the electron transport chain allows us to produce ATP. The problem you've got is that you can only shuttle hydrogen ions down the electron transport chain if you've got carriers available. And if you're producing hydrogen ions faster than you've got carriers available, then those hydrogen ions can't be shuttled and can't be used to produce ATP. And the hydrogen ions have a problem in the sense that if we've got hydrogen ions floating around, they start to interfere with the way in which the muscle contracts. So in order for a muscle to contract, generally what happens is that calcium ions are released into the sarcomere of a cell. The calcium ion attaches to what is called the troponin complex. By attaching to troponin, you reveal the tropomyosin complex, and you in essence get the myosin head attaching to the actin filament, and we get a muscle contraction. The problem is that attraction between troponin and calcium is outweighed by the attraction of troponin to hydrogen ions. The attraction for hydrogen ions compared to calcium is 238 times stronger. So if you've got hydrogen ions that for whatever reason haven't gone down the electron transport chain, they can interfere with the muscle, which reduces the amount of power that we produce, or the amount of force that we produce, because you've got less binding sites between the actin and the myosin filaments. So that's a problem. So one of the natural processes is that the hydrogen ions attach to pyruvate and produce lactate. And all you're reflecting in the change in the pH is really just a reflection of the increase in the hydrogen ion concentration, not the increase in the lactate concentration. So if we kind of look at this over a slightly longer period of time, here we've got two examples. We've got our 12-second example on the left. Now look at the 60-second example. So 60 seconds could be let's say, for example, an international track cyclist doing a kilometre on the track. And what you can see is the same thing applies, that you've got a significant increase in glycolysis after around about 10 seconds, in line really with the declining PCR concentration and the cell becoming more and more acidic over time because of the ever-increasing hydrogen ion concentration. We see the same thing whether it be really kind of short term, but in the short term we get a significant decrease in the PCR concentration. When it's 60 seconds, we do end up depleting it, but because it's 60 seconds, you'd be very foolish, wouldn't you, to go out as hard as you would do in 12 seconds, because you would, for want of a better term, you'd blow up. You have to judge the rate at which you want to use the energy. So you never run, for example, 400 meters at the speed at which you run 100 meters. You couldn't sustain it because the high energy phosphates would be depleted. So if you look at the speed of a 400 meter runner compared to a 100 meter runner, they are significantly different. Obviously, and this is why, because it's all to do with the availability of the substrates. Now, one of the reactions that we've not dealt with here is an additional reaction that is not often talked about, which is the adenylate kinase reaction. And actually, the adenylate kinase reaction does sit within the kind of the whole schematic that we've already looked at in terms of the energy pathways together. But it's quite an important reaction. So what we know is this: if we're doing intense periods of work, so we need to resynthesize or provide ATP very rapidly, it sometimes is not possible. And actually what happens is we start to produce ADP molecules, and we've got excess ADP. Remember that what we said was we try and attach phosphate to the ADP to resynthesize it. But if we're producing ADP faster than we can in essence provide phosphates to it, we'll have free ADP. Well, if you think about it very logically, if I've got two ADP molecules, I must by definition have four phosphates. Adenosine diphosphate has got two phosphates. Adenosine diphosphate in this hand has also got two phosphates. That gives me four phosphates. I only need three to make ATP. So this is the adenylate kinase reaction. So according to this reaction, ADP plus ADP, in the presence of adenylate kinase, which is the enzyme that drives the reaction, gives us ADP plus AMP, and AMP is adenosine monophosphate. So adenosine monophosphate. Now, what can't happen is this: you cannot take AMP plus AMP plus AMP and get ATP. Biologically, that doesn't work. But this is a way that we can form ATP. But this does come at a cost, because the AMP is then attached to some of those hydrogen ions that we've already been talking about. In the presence of another enzyme, which is AMP deaminase, we get IMP, which is inosine monophosphate, and ammonia, which is NH4. Ammonia leads to cellular fatigue. And actually what it does is the ammonia, again, very much like we've already been referring to, leads to a pH which becomes more acidic. And in part explains why that pH we've been looking at declines over time, because there's an increase in ammonia concentration. And remember that what we said was as the cell becomes more acidic, enzymatic reactions slow down. So the rate at which we derive the energy slows down. So although this reaction is very useful, it comes at a cost. So it's unsustainable. So in other words, again, explaining why you can't maintain high ATP turnover rates, that's the rate at which we use the ATP, why you can't maintain those for long periods of time. Because you're either going to run out of the PCR, or the cell is going to become acidic because of increasing ammonia concentrations, or it's going to become acidic because of rising hydrogen ion concentrations. So here we've got an example. Here we've got pie chart, and what you can see here is the relative contributions. This is in a 3-second sprint, so this is kind of how much energy is used in a 3-second sprint. Notice that the majority, not surprisingly, is from PCR. You've got some coming from stored ATP, about 10%, then glycolysis, and a small amount from aerobic contribution, even in a 3-second sprint. This is a really nice little panel. So this is from some work by Caddy and colleagues published in 1989. It's a very old study now, but what they've got is changes in muscle metabolites and pH during what they described as fatiguing exercise. So in panel A, what you've got is what I refer to as normal healthy participants. In panel B, it's just from a single participant, but it's quite nice, who is deficient in what is called myophosphorylase. So they actually don't produce hydrogen ions from glycolysis. Doesn't mean they can't produce hydrogen ions, they just don't produce them from glycolysis. What I want you to concentrate on, though, is panel A. So here what they've done is 3 by 15 seconds MVC. An MVC is a maximal voluntary contraction. It's isometric. So what they're being asked to do is push maximally against a resistance that doesn't work for 15 seconds. Then they recover, and then they repeat, then they recover, then they repeat. Notice there's some really, really key facts and points going on here. So point 1, notice that across the 3 repetitions, the ATP concentration in terms of millimoles doesn't change. And remember what we said, the whole process of substrate level metabolism is to resynthesize ATP. The second thing is, even though they've got recovery, the recoveries in this are fairly short. They're around about, I think, 30 to 60 seconds. I think they're about 60 seconds. That despite the fact they've got a recovery, the PCR concentration falls from around about 40 millimoles at the start to half of that by the end of effort 1. It falls by the same amount, well, half again, at the end of effort 2, and it falls by about half the amount again by the end of effort 3. So we've got a declining PCR concentration. I remember, if you're doing something like an MVC, you're being asked to push as hard as you can, then the energy is going to come from these instantaneous sources. At the same time, what you'll notice is that the concentration of phosphates is rising. So what's happening is that we are splitting ATP, but we are splitting it at a rate faster than we can reuse the phosphates. In other words, we're getting what's called free phosphates. Remember that what we want to do is take ADP, add it to a phosphate, add water, get take the phosphate, add it to ADP, okay, which gives us ATP, add water, that derives energy. But what's happening is that we are running this metabolic process is faster than we can use the phosphates, so the amount of free phosphates starts to increase. At the top, you can also see the relative pH in the cell. So you can see that the pH has fallen from about 7.03. By the time we get to effort 3, it's fallen to about 6.51. So that is telling us that the cell is becoming more acidic, indicating that there is being a contribution certainly from glycolysis, because that is where hydrogen ions are predominantly produced. So even though these are fairly short efforts, there is a glycolytic contribution, but it's also telling us that there's probably been a contribution here from the adenylate kinase reaction, because you've got an increase in ammonia, which again in itself causes the decline in the pH. And remember that as the pH declines, those metabolic reactions start to slow down. So the rate at which we derive the energy starts to slow down, which explains to a certain degree why, if actually they measured the amount of force, which we can't see on here, the force that they're producing would also almost certainly in each MVC start to decline. In this example here, which is from Greg Gaetanos, again, a fairly old study, which is from 93, what you've got here is we've got some data when they've done 6-second sprints. This is on cycloergometer. And what they've done is they've done 10 sprints of 6 seconds, and each sprint is then separated by a recovery period of about 60 seconds. And what you can see, even though they're 6-second sprints, you can see the change from across the first sprint, and then the change up to the 10th sprint. So have a look. One of the things that's quite interesting, if you look at the ATP concentration has declined. Across the first sprint, there's no real change. If you look at it across the 10th sprint, pre-10th, post-10, no real change. It has fallen, so it's gone from about 24 to around about 16. So it has declined, but we haven't run out of ATP. We're resynthesizing it. Notice, though, that what has gone up are things like the ADP concentration goes up after each sprint. So the amount of free ADP starts to increase. Look at the phosphocreatine concentration. It's gone from 76.3 at the start of sprint 1 to 32 at the end of sprint 1. By the time, though, we get to the 10th sprint, we start the 10th sprint at 37.5 and end at 12. So that's telling us that with repeat sprints, even with recovery, and the recovery is fundamental to this, the PCR concentration is decreasing. It's decreasing. Notice, though, that the creatine concentration is increasing. Remember that this is, we're taking the phosphate molecule off phosphocreatine to give it to ADP to make ATP. So we're left with what is called free creatine. It's creatine that just doesn't help us in the sense of it hasn't got the phosphates. Notice that its concentration rises from about 43.5 at the start of sprint 1 to 87.3. By the time we get to the 10th sprint, it's about 81.8. It goes up to 107.3. So a significant increase in the free concentration of creatine. Look at the glycogen concentration at the very top, declining from about 316 to 273 after sprint 1. By the time we get to the 10th sprint, it's much lower. It's at 221, declining a little bit to 201, so not as big decline. If you look at lactate concentration, this is muscle lactate, is rising from about 3.8 to 28.6 after sprint 1. By the time we get to the 10th sprint, it starts at 116.2, and actually, interestingly, it falls to 112. Now, we'll have to explain why that falls in a moment. But all of those are telling us that across a range of multiple sprints, you can see the way these substrate concentrations flux, that we're getting declines in the substrate, that's the glycogen and the PCR. We're getting an increase in the byproducts, so that is things like the ADP, the AMP, although the AMP doesn't go massively, the AMP, the PCR concentration declined, the free creatine, which is the byproduct, has increased, the lactate has increased, and so on. So you can see quite significant changes within a single sprint and across these multiple sprints.